Today we are going to talk about symmetries of circles. Let's first discuss the condition for betweenness. We're going to let pi be a plane and let A, B, C, and D be distinct points in pi such that B and C are in different open half planes determined by the line AD. And you can see I have it drawn over here. I have my line AD. And B is on the left side of that line and C is on the right. So they are in different open half planes. And then if the measure of angle BAD, which is here, plus the measure of angle DAC, which is there, and that's equal to 180, then A can be said to be between B and C. Since we're discussing circles today, it's really important to have an idea of the exact definition that goes along with that. For any point P and any length U, any positive real number R, and any plane pi such that P is an element of pi, the circle in pi with center P and U radius R is the set of all points X in pi such that the distance between P and X is equal to R. That is, the set of all points X in pi such that the distance between PX, the length of segment PX, is equal to R. And you can see that I've drawn this circle here. I have my center point P. Then the circle consists of all the points X that are the same length away, same distance away from P. And you can see I have it drawn there. In this case, my radius is R. All the points along the circle are exactly R units away from P. Next, I'd like you to do exercises 130 and 131. Press pause on your video, and when you're ready for the answers, press play again. So, how many reflective symmetries does my circle C have? It has an infinite number. You can see I can draw any line in the plane that goes through the center, and my circle would be a fixed figure under that line reflection. There are infinitely many. How many rotative symmetries does C have? An infinite number. Anytime I choose my center point to be my center of rotation, I can rotate that circle clockwise or counterclockwise any number of degrees, and it's a fixed figure. Next, I'd like you to try exercise 132. Press pause on your video, and when you're ready for the answer, press play again. So you can see here that if I have a line intersect my circle, it does not necessarily have to intersect in 2 points. It may intersect in exactly 1. When that happens, we say that that line is tangent to the circle. So here's the formal definition of tangent to a circle. The line L is a tangent to a circle C if and only if L lies in the same plane as C and intersects C in exactly 1 point. This unique point of intersection is called the point of tangency. So here, this is my point of tangency. Here's a property, C2. It says that if the circle C has a center C and lies in the plane pi, and if P is an element of C, then the line L in pi passing through P is tangent to C if and only if L is perpendicular to the line CP. So if I draw a tangent line to the circle at any point, what you'll find is that the radius drawn to the point of tangency is perpendicular to that tangent line. Now, I'd like to use that information to solve this problem. We are given that L is tangent to circle C at P here. PD, the length of segment PD, is 3, and the length of segment ED, not 2, 1. So ED is 1. I want you to determine the radius of circle C. Press pause on your video. When you're ready for the answer, press play again. To solve this problem, you had to draw in the radius from C to the point of tangent C. That would have told us that this radius was perpendicular to my line L. It forms a beautiful right triangle. So if I name my radius X, this length here is X, same thing as from C to E because it's also a radius. And now I can use Pythagorean theorem. So my hypotenuse squared, or the sum of x and 1, this whole length here, x plus 1 squared, has to equal legs squared plus legs squared. So I expanded x plus 1 squared here. I subtracted x squared from both sides. Then I subtracted 1, and I divided both sides by 2 to find my radius is 4. Next, we're going to talk about a regular hexagon inscribed in a circle. Since each angle of an equilateral triangle has degree measure 60, we can fit 6 congruent equilateral triangles together so that they share one vertex and only have a side in common with each neighbor, as shown on the right. So here I have all these equilateral triangles. Since all of the sides of these triangles have the same length, it follows that all the vertices apart from the common central one lie on a circle whose center is a common vertex and whose radius is the length of each triangle side. Furthermore, the straight line distance from one vertex to the next as you proceed around the circle will also be equal to the radius of the circle. This explains why the regular hexagon construction works. So we're going to talk next about the regular construction of a hexagon, and we can do that with a compass because we know that all of these points here are equally spread apart. We also know they're all going to lie on a circle since the radius from the center to each of these vertices is the same. So how do we do this? Well, the first thing we do is we draw a circle and mark a point on the circle. So we're going to take our compass, draw the circle, and then draw a point on that circle anywhere. With the compass needle on the marked point and without changing the compass radius, draw an arc like this. So I draw my circle, I leave the compass open the same width because remember that my points are equally spread apart. So I can put the point of my compass here and draw myself an arc. Then we're going to mark the point where the first arc meets the circle here. And we're going to repeat step 2 using the new marked point. So we're going to work our way around the circle till I have marks drawn all the way around. Once I get all of those points drawn, I can simply connect all the points on that circle and create my regular hexagon. A square may also be inscribed in a circle. If we draw a circle with center C together with one of its diameters, if we then construct the line through C that is perpendicular to the diameter, and finally we join up the 4 points where these two lines meet the circle, we obtain a figure like the one shown on the right. Clearly, this produces 4 congruent isosceles triangles whose hypotenuses are the sides of the quadrilateral thus generated, and all those hypotenuses have the same length. Each of the non-right angles in an isosceles right triangle has a measure of 45 degrees. So the degree measure of each angle of the quadrilateral we have produced is 45 plus 45 equals 90. Hence the quadrilateral is a square. So we can see I have a diameter here, I can draw another diameter that is perpendicular to the first and obviously through the center, since it's diameter. When we connect those points, I have created a square. So here are more specific directions on how to draw a square with a compass. So we start off by drawing a circle and marking the center C. After we've done that, using a straight edge, we draw a diameter of the circle here. Now remember, the next thing I have to do is draw another diameter to the one I just drew, so that it's perpendicular to it and goes through C. So to do that, you're going to follow the perpendicular through a point on a line construction from geometry, incidence, and transformations. We're going to draw the perpendicular to the diameter through C. So the way you do that is that you have your first diameter here. You move your compass so that it's not quite as long as that circle. Then you move your point, you mark the points on that radius. You move the point of your compass to the first one, draw yourself an arc, move the point of the compass to the second location, draw yourself another arc, and now we can draw our perpendicular line. So then once that's done, you join up the 4 points where the diameter and the perpendicular meet the circle, here, 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 and here. And now I've completed a square. We can also draw an equilateral triangle using our compass. This one's easy. We proceed as if we were constructing a regular hexagon inscribed in a circle like we did before, but at the end, we only join up every other point of the circle, leaving the in-between points unused. So again, we draw our circle, we mark a point, we keep our compass open, the same width opening, draw tick marks all the way around that circle. Then I connect 3 of these points, skipping every other one. And then I have an equilateral triangle. That concludes the lesson for today. I would like you to work on exercises 133 through 135 from EMF 16. Have a great day.